Yeah, so I'm talking about, you know, both like a general principle, which is that verification is cheaper than computation, and then sort of an example of that, which is this on proving pairings paper that was joint work with Andrea Novakovic from Geometry Research. Um, so yeah, I work at Alpen Labs. I'm Liam. Um, so just sort of to set this up, right? Blockchains allow settling smart contracts. We all know this. Contracts can be arbitrary programs, and we often think about the chain as like executing a program or computing a program. But I argue that really what the chain is doing is verifying the execution of a program. And verification is sort of fundamentally simpler than computation. This is like a really deep fact that underlies a tremendous amount of computer science and snarks, the reason they exist at all. And I think it's underexploited. Like we can take more advantage of this fact. So I don't know if this is kind of like a hot take, but like there's this sort of ZK VM trend where, right, you can execute a program in ZK. And that's leaving some stuff on the table, which I hope to argue for. Yeah, so I think it can be further exploited. Yeah, and we use this for the pairing paper. I'll talk about pairings more in a minute. Yeah, and why you should care about pairings. And by pairings, I mean elliptic curve pairings. I think many people probably heard of them, but they're equivalent or sufficient to construct universal snarks. And so snarks allow us to verify any computation, and pairings allow us to verify snarks. So in some ways, pairing verification is like the fundamental missing piece, and that's what we need at Alpen on Bitcoin, for example. So this is the sort of very fundamental essence of why verification is cheaper than computation. So there's this complexity class of problems called P, which stands for polynomial time. They're efficient to solve. There's a much bigger class of problems called NP, which stands for non-deterministic polynomial time, which are efficient to verify. There's this big sort of open question, right? Does P equal NP? Certainly it doesn't seem like it right now. And there are many problems that are known to be efficiently verifiable or efficiently checkable, but not efficiently solvable. And so this is what I mean by verification is fundamentally easier than computation. And so one thing you can think of when I say non-deterministic, right, like what does that mean? I think sort of technically, right, you can imagine like the program, you sort of explore all paths at the same time. But another way to think about that is you have a program that checks something and you're just sort of guess the right answer, or you have a hint that tells you which path to take when, say, solving a satisfiability problem. And so snarks are built on NP relations. And so we already do this, actually, all the time in designing snark circuits. And SNARK stands for Succinct Non-Interactive Argument of Knowledge. It's sort of synonymous with zero-knowledge proof, but it's a little bit more specific term. So one very simple example of this is computing divisions, right? I think most people probably would agree, even by hand, computing divisions is harder than computing multiplications. It's certainly in circuit, if one wanted to compute a division, it'd be very expensive. You have to do like extended Euclidean algorithm or some kind of weird exponent thing. But thankfully in snarks, we never have to compute divisions. We can just sort of know the answer ahead of time and check a multiplication instead. So here we verify instead of compute a division. Same sort of thing for square root, right? Computing square roots is hard. Instead, we just check that the square of what we claim is the square root equals the thing we're supposed to be square rooting. So in both cases, we take this complicated operation and just reduce it to a single multiplication. And these are very well-known tricks. People do them all the time. But how far can we take this intuition. And just to be clear, right, like these aren't asymptotic improvements, these are constant factor improvements, I think. Yeah, maybe slightly asymptotic, I'm not sure. But the P versus NP thing is fundamental, like it's an asymptotic improvement. Like I said, we can reduce the verification of arbitrary programs to verification of pairings. And the way we do that is with snarks. And a snark is a way to prove that we know something, right? So a snark stands for succinct non-interactive argument of knowledge. And there can be sometimes a little slippery to get a handle on, but it's a way for me to argue that I know something to you. In this case, it would be W. So as like an example, right, suppose X is like a block header and W is a block, and I want to argue that I know a block that is valid without telling you what it is. This is exactly the sort of problem that a snark would allow us to solve, and people do this. And you can construct it for arbitrary relations that are efficiently checkable. Remember, NP is the same NP from before, it just means we can check it. So anything you can efficiently check, you can construct a snark for, or represent as a circuit. All of these things are equivalent. We know how to construct snarks with constant proof sizes and constant verification complexity from pairings. There are a huge number of snark constructions with lots of different properties. The ones that we get from pairings that are constant size all have trusted setups, although in the case of Planck, Flonk, and Marlin, they're universal and updatable, but doesn't really matter for our purposes now. And the point of this is just that if we can verify a pairing, right, efficiently, say on Bitcoin, which is not trivial by any means, then we can verify a snark, and through a snark, we can verify a program of arbitrary complexity. So this is sort of why we're interested in pairings at Alpen. So to talk about the paper, like a little bit, right? Most people treat pairings as a black box. They treat elliptic curves as a black box. They're kind of scary and mathy. And I won't get into too much of the math, but just to sort of set it up for you guys, we'll take an elliptic curve over a finite field. So this could be like BN254 or BLS381. You may have heard of, these are curves with pairings. But there are other curves that don't have pairings. And the cool thing about elliptic curves is that we can add the curve points. So an elliptic curve is a curve, right? You know what a curve is. There are points on it, and we can add them together, and they form a group, meaning that it's associative and commutative, and there's an identity and an inverse, and it sort of behaves in the way you would expect addition to. And we usually are concerned with points of finite order because we're working over a finite field. So that just means if you add the point p to itself r times, you get back to 0. One sort of crucially important thing about elliptic curves in general is that you cannot multiply points, right? So you can add numbers, you can multiply numbers. You can add points, but you cannot multiply points together, right? There's no distributive operation over point addition, unless you have a pairing. That's what pairings allow us to do. And that's sort of why they're really cool. Just some technical details. We have another point Q. Both of them lie on the curve. The little to the K means it's like in a bigger field. But yeah, the pairings allow us to sort of multiply curve points once. So here, A times P means we add P to itself A times, we add Q to itself B times, and when we pair them together, it's the same as sort of raising the pairing of the 2 points to the product of A and B. And we can use this to build all of the cool cryptography that we know and love, like polynomial commitment schemes and BLS signatures and other stuff. So how do pairings work? And this is where the kind of verification is cheaper than computation comes in. So when you treat pairings as a black box, you sort of given an algorithm for computing a pairing, and you don't think about it maybe that much because it's, complicated. But if we break it down into simpler parts, we can find places where instead of computing things, we can provide hints in the right way to accelerate the verification of pairings. So pairings have two parts, the Miller loop and the final exponentiation. Just a technical detail here, we're talking about the Tate pairing, or really the optimal Tate pairing, or the 8 pairing. There's also the Vey pairing, which is related but different, but everybody uses the Tate pairing. So this is expensive in large part because all of the computation you do when you're computing a pairing is over an extension field. But it's very highly structured. So how can we verify it more efficiently? So the paper will sort of explain all of this, or if you want to come up and ask me later, I can explain it too. But the first part is we're able to completely eliminate the final exponentiation using clever use of hints. What we're really doing via the final exponentiation is checking that the output of a pairing is an R residue, meaning that it's like something raised to the R. So saying that, I mean, maybe it's not that surprising that you can, instead of just doing the final exponentiation, you could just provide the rth root. This is a different sort of subgroup membership check. We take this further, and these techniques are kind of like known, or to some extent known in different parts of like the pairing literature, but they don't seem to have been adopted very much in the sort of SNARK, or I guess blockchain broadly, world. So I mentioned the 8 pairing. There's this really cool trick where you can write R as like a more efficient to compute thing. But in any case, we're still providing this value h, which is like the kind of rth root. And so we can check this raised to the r much more efficiently than computing the final exponentiation. And it turns out that has the same structure as the pairing, and so goes even further in the paper. For the Miller loop, each iteration of the Miller loop is evaluating a line at a point. And the interesting structure here is that when we have a pairing, the line depends only on the second point. So in many SNARKs, for example, the KZG-based SNARKs, the second point is always fixed. So we can pre-compute all of the lines and verify the evaluations of the lines more efficiently than if we were to compute all of the lines as we go, which would be sort of the normal, or I guess more obvious way to do it. And finally, and this is probably the clearest example of verification over computation. Remember I said we're working over extension fields. Elements of extension fields are known to be sort of in correspondence with polynomials. So any kind of arithmetic that you perform in an extension field, you can also represent as polynomial relations. And there's this very, very common trick in SNARKs, where when you have polynomial identities, you can check them at a random point, and if it holds at a random point, then with overwhelming probability, it will hold as polynomials. And so we do exactly this to reduce the extension field arithmetic to just a bunch of polynomial identities. And this saves a lot. And so the two main applications of our work of verifying pairings are definitely recursive SNARK verification or proof aggregation. So in many cases, you can avoid verifying pairings, but you can only sort of push it so far. You can kind of combine pairing checks, so you only have to do one, but eventually you will have to check a pairing if you want to do general recursive proof composition. And so for example, right, if you have two completely unrelated proof systems and you want to verify a Groth 16 proof inside a Stark, you will have to do a pairing check in circuit. And you could use these techniques in that situation. And the other kind of interesting example is verification on blockchains, like I mentioned. I am specifically thinking of verification on Bitcoin, because as you may know, Ethereum has a precompile for pairings. So you don't really need to do much to verify pairings on Ethereum. Verifying pairings on Bitcoin is not possible at all. And so you need something more. You need probably like BitVM, or maybe if we are able to activate cat, opcat, like string concatenation plus integer multiplication. But in any case, all of these tricks really go very far in these extremely highly constrained computing environments like Bitcoin. So yeah, on-chain verification of pairings, which we would want for a ZK rollup on Bitcoin, is ridiculously expensive. It's just not possible. So the BitVM2 team is using these tricks to, hopefully make something that works in practice. And yeah, like I said before, right? Pairings enable snark verification, enable arbitrary verification. So this is like that one little bit where you like cross the distance and then you're kind of everywhere. So yeah, I mean, I think this is kind of an interesting direction to explore. This like breaking down things instead of treating them as black boxes and seeing where can we verify steps more efficiently than just compute them directly. I mean, there is an advantage to this sort of VM approach, right? Because there's less development effort, right? You have a program, you just compile it, you prove it, you're done. But for things like pairings that are very expensive and maybe things that occur very often, I think this approach is worth considering. Lots of expensive computation happens on blockchains. Maybe there's a way to check it faster than to do it. Lots of expensive operations and snarks, for sure. And so I think it's an open question how far we can take this kind of motif. And that's it.